Group 4, please start presenting.
Good morning, to everyone. I'll be presenting on scattering parameters, but dealing with the shift in reference planes and also about the power waves. Is my screen visible? Oh, okay. So, uh, So we had my previous group mates had already tackled the scattering parameters. So here we are just looking at shifting where the signal gets into the network and how it affects the output and all that. So because scattering parameters relate to amplitudes of traveling waves that are incident and reflected, the S11, S12, all that. So the reference planes must be specified for each port in the network. So here we learn how the transformation happens when you're moved from the original locations. So consider an N-port microwave network shown where the original terminal planes are located at Zn is equals to 0 for each port. So here it's Z1 is equals to 0. And here, just as the ports increase, so does the location shift towards the 0. So Zn is just where the signal gets into the network, as you can see, be the incident wave and the reflected wave leaving from that point. And then, so consider a new set of reference planes defined at Zn is equals to Ln for the nth port. So consider that now you're shifting where you're inputting the signal to this point here. And now you have to also define a new scattering matrix, and it will be denoted as S bar. So, well, yeah. So in terms of the incident and reflected voltages, you get the reflected voltage is equals to S V positive at the original input port plane. And so when you refer now to the new plane, you get this formula here. And then the new voltages relate to the original ones by multiplying by a factor of e raised to power j theta, where theta n refers to is equals to beta n ln, which is basically just the electrical length as you shift outwards. It refers to this difference between the original and the new reference plane. Yeah. So that's what you get. And this is just substituting the relation into the first formula, excuse me. And yeah, so after all that, you get that the result is the new scattering matrix is equals to e raised to power negative 2j theta n for S and N. S and N, as my previous group mates had talked about, is just the reflected, the scattering parameters for the reflected when it's reflected in the same port. So that means that it will travel the same electrical length twice. As you can see here, if it's reflected back, if it travels to and from, it will cover this distance twice. Yeah, but if it's just traveling to any other port, it will cover the distance once. So if in that case, it will just be multiplied by a factor of e raised to power negative j theta. Yeah. So I'll go to power waves and general scattering parameters. So in this case, if we have a load impedance equal to the characteristic impedance of a transmission line, the power of the incident wave, all of it is delivered to the load. Yeah, this one we have come across it. But when the generator impedance does not equal the characteristic impedance of the transmission line, there's no impedance match for maximum power transfer. So these power waves come in to help attain the maximum power transfer. Yeah, so it's possible to introduce new voltage and current variables and corresponding wave amplitudes that result in conjugate impedance matching conditions. This is what we use so that you can get the maximum power transfer in all in these situations. Yeah. So consider the figure below where there is no transmission line present between the generator and the load. As you can see, it's just from the generator and then the generator impedance straight to the load. Yeah. So there's no characteristic impedance for the transmission line, no reflection coefficient, and incident or reflected voltages. So in this case, especially when VL is complex and VG, you can define a new set of waves called power waves, which have useful properties when dealing with power transfer between the generator and the load, as well as to problems with the lossless or lossy transmission lines when Z naught is complex, the characteristic impedance of the transmission line. So these are the variables that we use. So the incidence and the reflected power wave amplitudes, A and B, are defined as the following linear transformations. So A will be now our incident wave. So this is how it relates to the voltage and current in that circuit, and also B the same way, just that it's negative because it's reflected. Yeah, where ZR is known as the reference impedance and may be complex. And so the power delivered to the load in that case is a half real of the real part of V I conjugate. This is also what we use to calculate power normally. So this is what you also get, where it means that the power delivered to the load is the difference of the power transmitted between the incident wave and the reflected wave. Yeah. Normally it's V positive at A and V negative at B, but now with power waves, yeah, this is what we use. An example, or rather an illustration to show that the formula works. So from basic circuit theory, the voltage, current, and load power for the circuit shown for the connecting the signal generator to the load directly is given as V. So V voltage across the load is given as V naught L over ZL ZG. I is just this divided by the load, and yeah, and power is just VI. So this is what we normally use to get power across the ZL. So when using now the power waves formula, so here we set the reference voltage to the conjugate of the reflected of the load voltage, so that the reflected wave goes to zero. So here substituting the previous values we had gotten for V here and for I, and also for ZR, the reference voltage to conjugate, you get A as shown, and also B tends to zero. So because B is already zero in the first formula for power, that one now only remains as a half the magnitude of A. So that, as you can see, this formula is just the same as the initial formula that you were working with. Yeah. So with that, I come to the end of my presentation. I just have this is a vector network analyzer. My previous group mates had also touched on it. So it's used to measure the scattering parameters of the network under test. So this is the device under test, and this is the port 1 and port 2 that we normally hear. So inside here, there's a signal generator that now feeds a signal here into the network, and now the output network is then analyzed against the original signal, so that you can now get all those parameters and other things like phase and magnitude. Yeah, and the signal is plotted here as you're seeing in the display. Yeah, so by analyzing the transmitted and reflected waves in the network, and there's a switch inside here, so that now you can shift between the reflected measurements and the transmitted, like S11 and S12. Yeah, you can use the switch to change between the two. With that, if there are any questions, you can ask them. Otherwise, thank you for your time.
Thank you, Agnes. Is there another presentation from Group 4?
Yes, they'll be presenting shortly.
All right.
I hope you can hear me.
Yes.
So I'm going to present on signal flow graphs. From here, it says that it's an additional technique useful for analysis of microwave networks in terms of transmitted and reflected waves. So it's another technique that is
Uh,
used.
just a minute. Could you please zoom in?
Oh, is that okay?
Yes.
So this technique is used in is another way of solving the scattering parameters. So um, I'll use this whiteboard to explain the things that are in that PDF. So in this first diagram here, it is a two-port network which contains the scattering parameters, and in this second diagram is how you draw the signal flow graph. So yesterday Sam explained about the coefficients S11, S12, S21, and S22. So S11 was the reflection coefficient from port 1. So it's here. I hope you can still see.
Yes.
Then S12 was the transmission coefficient from port 2 to port 1. So from here, so it goes like this. So this is S21. So it's so you write it in a way that it's to where it's going from where it's from. I hope that's understood. And here is S12, and this is the other reflection coefficients. So A1, B2, and B1, A2 are nodes, and these lines connecting them are branches. So S11 is equals to B1 over A1. So as I said, the denominator is where it's originating from, and the numerator is where the branch is going to. So using that knowledge, S1, 2 will be B2 over B1, sorry, over A2. Yes, so and S22 is B2 over A2, and S21 is B2 over A1. I hope you have understood that. Yeah, so these A1 and A2 are incident to the ports, and B1 and B2 are outgoing. So um, this is what I have drawn there. I hope you have understood how to draw the signal flow graph. So I'll jump to the decomposition first because I've already said about the key aspects, the nodes and the branches. I'll go to decomposition of the signal flow graphs. So there are rules. Go back to my whiteboard. Um, so there are four rules used in decomposition of the signal flow graphs. One is the series rule. So V2. So at this branch here, it will be S21, and this branch here. So for the series rule, we'll take here V2 will be equal to S21 V1, and V3 will be S32 V2. So at this outgoing port here, V3, it will be S32, and substituting V2, it will be S21 V1. I hope up to there it's okay. The next one, so for the parallel rule, let me draw first. So let's say here is V2, let's say here is V1, and here let's say it's SA, and here is SB. So solving it to bring one branch V1, V2. So V2 will be equals to V1. So you add the branches SA plus SB. Yeah, that's for the parallel rule. So if you notice, for the series and the parallel, the branches are in the same direction. So you should take note of that. Then um, there is the self loop rule. So in this rule, let me first draw the diagram. So V1, V2, V3. So here we said is S21, and here is S32. So for the self loop rule, yeah, this is S22. So for this rule, um, first we'll say V2 is equals to S21 V2, V1, sorry. Plus, there's another branch there which is looping at the node V2. So S22 V2. So, but V3 will remain S32 V2. That one will be like that. So combining the terms together, so V2 will be S21 S21 V1 1 minus S22. So that, and so when you come to solve for V3, it will be, you will just multiply. Yes, I hope it's clear up to there. And for the last rule, it's the splitting rule. So let me first draw the branches. V1, V2. Yeah, let's put V3. And here is another node, V4. So here we say this S21, S32, and S42. So how we'll split this network. First, I'd like us to notice that at this point where we are splitting, there is one incoming which is this S21 and two outgoing, which is S42 and S32. This we'll see in an example to come how it's useful to know how to determine the node at which we'll split. So I'll fix that one later. So here is V1, V2, V3. So here is V2 prime, V4. So this node are typically the same. So it's S21 and S32, S42. So after splitting, so V2 will be equals to S21 V1. So it's like the same for here also because I said V2 and SV2 prime are typically the same. So V3 will be S S32 S21 V1. I hope you understood how I've solved for V3, just substituting V2 which is S21 and S21 V1 and V4 will be S42 S21 V1. So basically, those four rules will guide us in solving problems using the signal flow graphs. So as we point towards, so this I've explained all this. I'm using those drawings. So we'll go to this example. Um, use signal flow graphs to derive expressions for gamma in and gamma out for the microwave network shown. So let me solve it here so we can go together. So the diagram, I hope you can still hear me. This is so we have been told to solve for here. So We'll first start by drawing our signal flow graph. So this is A1, B2, B1, A2. So these branches over here. But from our diagram here, you can see there is an impedance connected. So we'll add that in our graph. And we can see it's from B2 to A2. So that's our signal flow graph. Let me indicate the coefficients to so we'll start by applying those four rules that we had. And if you remember, I mentioned um, when we use the splitting rule, the node which we are supposed to split, um, it should have a one incoming branch and two outgoing branches. So at this node A2, it's the one we are going to split. So let me draw it well so that we can see. So here S21, S22, S11, S12, and here so you can see at this node there is one incoming branch and two outgoing branches. So that's the node we'll use and apply the splitting rule. So it will be like this. So you remember that at this point here it will be like A2 prime, which is the same as this one. So B2, B1. And so here, we know that B2 to A2 prime is gamma L. Here we'll change it and it will be gamma L that goes through, and here um, will be our S22. Yeah, so to solve this part where we are split, we can see that it is in series. So when we solve in series, at B2 it will be S22 multiplied by, it will be like that at B2. So as we have solved that at B2, we see that we have a self loop. Here is S21. So I hope we are at par up to here. So for the self loop rule, we know that if we multiply from this point up to here, let me return to the self loop rule. So let's say we are from here to here, so our V2 will be S21 over 1 minus S22. I showed you how to derive it. So at this point B2, it will be like this. So at this point here will be S21 over 1 minus S22. This is the one B2. A2 B1. Remember here is gamma L, and here S12, and here S11. So we see that from this point here, they are in series up to S12. So solving that, We know when they're in series, we'll just multiply. So it will bring us S1 S1 to S21. We should not forget this one. O over 1 minus S22. So the equivalent circuit will be so up to there. Is everything okay? Okay, we'll continue. So here we can see that it is in parallel, like this. And for the parallel rule, so for the parallel rule will add. So S11 plus S12 S21. So let us see the. So it's like this. Yeah. So up to there, is there any question? So I'll leave you to solve for the output part following those decomposition rules. And so let me go to the applications of signal flow graphs in microwave networks. So the first one is network analysis. So they simplify complex microwave circuits by converting S parameter matrices into visual representations. I hope you have seen that where, when we were solving the problems. So the second one is they provide an intuitive way to apply Mason's gain formula to calculate the overall transfer function of the network. They can also be used for impedance matching and reflection analysis, and lastly for stability analysis. Yes. So I think, yes, I've come to the end of my presentation. So is there any question?
Thank you. Do we have will we be expecting another presentation from group 4 next week?
Yes, there is one more.
Oh, okay. I've seen Dr. Kon is in the meeting. I'm not sure if we should wind up now that we are done with the presentations for today.